So our next speaker is Hyojin Park of Seoul National University, presenting lightweight video object segmentation with adaptive template attention module and temporal consistency loss. Thank you. Go ahead, Hyojin.
Hello, everyone. My name is Hyojin Park, a Ph.D. candidate of Seoul National University. Today, I will talk about video object segmentation. What is semi-supervised video object segmentation? This task is tracking a target by mask from a given annotated mask above the first frame. The model consists of feature extraction, finding object by embedded target information, and finally, generating mask and the target information. This is initialized by the given condition. So tracking by mask is essential for many applications because we can get accurate object shape rather than just a rough bounding box. There are two main issues. First, the object shape is changed at every frame, and finally, the shape is totally different from first frame. Second, a model has to preserve consistency of the mask even there are similar objects nearby target. In this paper, our contributions are: first, we propose a new lightweight VOS model for mobile device. Second, we combine two different template matching strategies. One is a short-term for localization. The other is a long-term matching for accurate mask with using previous heatmap for attention crew. Heatmap means probability map of target. Finally, we also devised new temporal consistency laws for decreasing the error propagation problem. So our models show fast speed and good accuracy than other video segmentation models. For solving this problem, there are four popular approaches. First, template matching is constructing target template and compare with input feature map for measuring similarity. This method is faster than others, but low accuracy. Second, online learning is fine-tuning model parameters in inference stage. This method easily becomes a specific model and achieve high accuracy, but training in inference causes slow speed. Memory network is the which this model shows accuracy, but fusion loss three. Many model uses this vector for online document feature. This vector consistency of mask well across optical flow requires heavy computation. Third matching, model generate instance Shortterm template for target like rough mark. Making an instance Shortterm template, the model takes previous frame feature and concatenates with previous feature for sufficient known information. After making template, model compare and current feature template for producing similarity. However, using only short-term matching incurs two problems. First, overly dependent on previous result increase error propagation problem. Second, using small and instant feature map is harder to generate accurate mask. For those reasons, we also devised adaptive long-term template by template attention module. Here, we produce a long-term similarity map between the long-term template and Raji current feature map. For doing this, a current feature map is changed to XT by previous heat map and convolution layers for separation of some pixels information which are far from previous mask. After then, XT become query feature map. The template attention module produces attention map between template and this correct feature map by matrix multiplication. Finally, the attention map 80 is concatenated with the modified feature map, and they are blended together for producing final similarity map. So how to manage this long-term template? We assume that pixels inside a target object have a distinct embedding vector distinguished from non-target object pixels. Our model is designed to find this vector by self-attention and summation of long-range frames information with a less related one of the target. We reuse already extracted feature map with current estimated heat map. Many methods re-extract feature map again for updating template or memory after concatenating with estimated mask and input frame. However, our model reuses feature map again, therefore, the flow for updating is really tiny. For updating template, we use a template attention module again. First, irrelevant information in feature map is suppressed with current estimated heat map as attention clue. Second, making representative value by matrix multiplication following similarity pattern across channels. For example, the hexagon in left indicates the related information region by attention clue, and thus the gray outside of the hexagon represents suppressed information. After that, we can compare only important region across each channel's plane. If the two planes are similar, the result value is high, like red pixel. If not, the value will be low, like blue pixel. Finally, we have a template matrix as I. This one is weighted average with previous template for updating. Our templates are constructed based on estimated result along the entire executed frames. Therefore, when the template is updated with incorrect result, it will gradually lead to incorrect tracking and makes error propagation problem. To decrease those problems, we design new template constancy loss based on novel definition of transition matrix. The transition matrix means changing tendency from previous frame to current frame. So this is produced from the long-term similarity by just a single conversion layer. For training the model, we devise new ground truth by using estimated and true mask rather than using only true masks. So this is the ground truth mask of two consecutive frames. And this is the estimation result. And we can observe many false regions by blue marking. This is visualized transition matrix, and white color means change to foreground, and black means change to background. Finally, gray indicates the same class regardless of foreground or background. So if we use two original ground truth masks, the model cannot learn how to correct false region, just to preserve it. However, when you use previous estimation and current ground truth mask, the model can learn how to correct, for example, this black region. By using this new ground truth, we add temporal constancy loss for training model with L2 loss. So in summary, first, model extract feature for tracking every target. The model conducts short-term matching. After that, calculate the long-term matching and estimate the transition matrix. We use cross-entropy loss and temporal constancy loss for training. Decoder generates a final mask with similarity map and feature map. We use conv transpose and pixel shuffle. Finally, model update each template, and this is the entire our model. We evaluate our method by widely used the Davis benchmark. Davis has two tasks. Davis 16 is for single object scenario task, and Davis 17 is a multi-object scenario task. And first, we pre-train model with salience detection dataset and TTVOS dataset. After then, train with the Davis. Our models show higher accuracy than Cheyenne mask, also show similar accuracy but much faster. The first population study, we compare each module's role and advantage. Experiment 1 using only short-term matching and experiment 2 using only long-term matching. In result, experiment 1 show high accuracy in Davis 17, but experiment 2 has a high accuracy in Davis 16. This means that first one keep object ID, but fail to making an accurate mask. But second one show performance degradation on multi-object tracking task due to failure in maintaining object ID. Even it generates more accurate mask than experiment 1. For example, experiment 1 preserve object ID but lose horse leg. In experiment 2, it makes accurate shape but lose green object, the rider ID. Experiment 3 get every advantage from both temporal matching method. Also, when we add temporal constancy loss, we increase more accuracy for both tasks. Recently, we add better attention clue and adaptive weight value for updating Longterm Template. We success to improve accuracy more again. We also apply our temporal constancy loss to another model. The below table shows improvement accuracy. The improvement is higher in Legend 18 than Legend 101. So this is the result video. Additionally, we conduct further applying about long-term template and transition metrics. Using two models, we quantify the object movement, and when the movement is little, like this situation, we skip network to reduce computation, like here to here. So finally, this shows we successfully improve speed 2 times more than baseline without any performance degradation. So thanks for listening, and the code will be released soon in here. Also, I really appreciate the Facebook about giving great internship chance and valuable discussion for me. Thank you.
Thank you, Hyojin. So I don't see any questions on the board, but for the audience, if you do have any questions, please go ahead and post those, and I'll relay them to the speaker. But I do have one question about the. You mentioned early on that you did semi-supervised loss on distinguishing pixels of the target versus non-target pixels. And
Yeah.
can you talk a little bit more about how you propagated that information about target versus which pixels were target versus non-target to make that semi-supervised method work?
So in this data set, the given is the only first frame, but at least every frame have a ground truth mask. So in the training, so we have a ground truth mask and using cross entropy loss for backpropagation by making gradient. So basically the loss is similar to the other segmentation task. But the class is just foreground about any class and the background. So it is kind of some binary problem.
Okay, but you did start with a ground truth mask is essentially like a label, right?
Yeah, so that is kind of some, okay. Yeah, so here, so at least the task, what is a target object? So target object is provide as a mask, like, just a second. So here, so only, so any type of class, the task give us some target mask. After that, the input is just any frame. It's just the RGB frame. So after that, using this given condition, we making some target information. After then, we finding this same target from the input RGB frame. So in the inference time, we don't use any mask, only the given mask, just a kind of some condition and what is our desired target.
Okay, thank you. All right. In that case, I don't believe there are any other questions from the audience. So I think we can go ahead and move on to our next speaker. Thank you very much, Hyojin, for the talk.
Thank you.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. Ada Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. EMSA. Gray Matter Labs. Greenwaves. Hymax. Imagimob. Latent AI. Maxim Integrated. Quixo. Reality AI. SensiML. Silicon Labs. Sentient. Google TensorFlow. XMOS. And lastly, silver sponsors, Edge Cortex, Hotchi, and Synsense.